Welcome to the lab, everyone. As the senior scientist, I'm absolutely thrilled to be your guide for today's explainer. Think of this as a sort of masterclass into how we deeply explore, question, and ultimately understand the truly fascinating natural world around us. We are moving way beyond just wondering about things and stepping right into the rigorous, exciting realm of secondary science. Let's get started.
Okay, let's do a quick run-through of our flight plan for today's exploration. We've got 1. The explorer's conceptual tools. 2. Simplifying reality through models. 3. Practice, building your models. 4. Precision in the global lab. 5. History behind scientific symbols. And finally, number 6, from guesses to predictions.
Starting off with Section 1, the explorer's conceptual tools. Here is a little professional tip for you. Any good scientist needs a foundational toolkit to tackle the complex chaos of reality. You just can't walk into a laboratory or a rainforest empty-handed. So as we begin, I want you to keep two key conceptual tools in mind. First, the magnifying glass. This represents careful observation. It's all about noticing patterns, looking incredibly closely, and paying attention to details that most people might completely miss. But observation just isn't enough on its own. We also need the compass. The compass reminds us that observation needs direction. We really have to ask the right questions, choose the appropriate models, and know the exact limits of where our ideas apply. Science isn't about wandering aimlessly. It's about exploring with intense care and focused purpose. Moving right along to Section 2, simplifying reality through models. You see, reality is simply way too complex to study all at once in full detail. Honestly, it's overwhelming. And that is exactly why scientists rely so heavily on simplification and modeling to actually get their work done. This brilliantly illustrates how our specific goal dictates what details we intentionally drop. As someone who has spent years in the lab, I can tell you that sometimes ignoring things is literally the smartest move you can make. For example, in physics, if we want to understand the path of a moving car, we might represent that entire massive vehicle as just a single tiny dot on a graph. Or if we're creating a model of a falling object to study gravity, we deliberately ignore air resistance just to isolate gravity's true effect. These aren't mistakes, right? They are deliberate, calculated choices to simplify really complex research. Let's look at a really fun example, predicting if a cricket shot will go for a 6. We want to know if the ball will cross that boundary without hitting the ground first. To build this model, we have to ignore all the unnecessary details. The brand of the bat doesn't matter at all. The color of the ball, totally irrelevant. The exact amount of grass on the field, ignore it. Instead, we focus strictly on the absolutely crucial factors that actually impact the flight, like the mass of the ball and the speed and direction it was hit. It's a perfect example of how models deliberately ignore unnecessary details to give us clear, actionable answers. All right, on to Section 3, practice, building your models. Let's put this into practice and build up your own scientific reasoning. It's your turn to think like a scientist. I want you to construct a model of a simple daily task. Let's say the time it takes for a bicycle ride from school to home. Here's a little template to help you out. First, define your key variables. What matters most here? Is it your speed, the total distance? Then, I really want you to brainstorm and explicitly justify which environmental factors you're choosing to keep and which ones you choose to ignore. Maybe you completely ignore the color of your bike, but you definitely keep the number of traffic lights on your route. Explaining exactly why you ignored certain factors is exactly what scientists do every single day. Let's challenge ourselves a bit further here. Look around your house and try to list 3 daily items. If you were going to study them, what details would you simplify them into for your models? Or think bigger. What measurable variables would you define for a model of a school trip? What about a common sports game, like football or basketball? Try to identify the variables in a sports game model. What are the key elements you keep, and what details do you throw out? Which brings us to Section 4, precision in the global lab. So once we build these amazing models, we have to share them with the world. And that requires incredibly precise, standard scientific language to avoid dangerous global miscommunication. To show you just how high the stakes really are, consider this terrifying number. A passenger aircraft once fell 15,000 liters short of fuel mid-flight. No way, right? But it happened. Why? Because the ground crews calculated the fuel density in pounds per liter instead of the standard kilograms per liter. Thankfully, the plane managed an emergency landing, but standard units prevent historical errors like this airplane fuel incident from happening in the first place. Precise language literally prevents deadly ambiguity. Avoiding that kind of ambiguity by using a standard unit like the kilogram not only prevents those massive historical errors in aviation, but it ensures absolute fairness in international research and everyday global trade. When you buy vegetables, a kilogram means the exact same amount everywhere on Earth. Standard units ensure that whether a scientist is working in Mumbai or Montreal, they are speaking the exact same precise language. Let's dive into Section 5, History Behind Scientific Symbols. Now, you might be wondering where this precise shared language actually comes from. Well, often, scientific symbol choices aren't just random letters we pulled out of a hat, they honor very deep historical roots. For example, look at how international agreements rely heavily on historic Latin terms. Take the speed of light, which we always denote with the lowercase letter c. Why c? It actually comes from the Latin word celeritas, which literally means speed. These historic Latin terms and international agreements shape our modern scientific symbols, helping scientists perfectly maintain consistency across all global research. And finally, Section 6, From Guesses to Predictions. To wrap things up, let's elevate our exploration to see how we turn everyday casual guesses into robust scientific predictions. It is absolutely crucial to understand that in science, theories are reasoned expectations based on massive amounts of measurable evidence, not just simple guesses. And a key strength of science, maybe the best part, is that we constantly update our models when new evidence challenges old theories. If our predictions don't match our observations, we don't just ignore the new data, we adjust and refine our models. For instance, imagine looking out the window and saying, "Oh, it's going to rain today because the clouds look pretty dark." That's just a casual hunch, right? It's completely unreliable. But meteorologists use concrete, measurable evidence, like humidity being over 80%, exact wind speed and direction data, and trackable temperature drops to predict weather patterns. These predictions are far more reliable than hunches, precisely because they are built on hard, trackable data. We use this evidence to actively anticipate events before they even happen.
So, using your magnifying glass for careful observation and your compass for guided direction, I want you to really think about this. What measurable evidence would you need to actually collect for a school science project to accurately predict your own local rain? How do you move past everyday guesswork and hunches into true, rigorous science? Science is an open invitation to question, to measure, and to model the world around us. Thank you so much for joining me in the lab today. Keep asking those great questions, and I will see you in the next explainer.